All right. So this is where we were yesterday. I had you just write down 1 through 10 what the organic prefixes are. I keep telling you that organic is a completely different field, including even the system for naming. When we named ionic compounds, named molecular compounds, we got the hang of it. And for molecular compounds like CO2 is carbon dioxide, you use the di. But when we get into organic compounds with just carbons and hydrogens, like this, we wouldn't call that carbon tetrahydride. I mean, according to the molecular systematic naming structure, that's what we would call it. But in organic chemistry, it's got its own system. It's called methane. Because there's one carbon, we always use meth for one carbon. If there's 2 carbons like this, we always use F for 2 carbons. And we build around those organic specific prefixes. Now, 5 through 10, 10's not on here, but that's deca. We know those. That's from geometry and from what you learned before. But 1 through 4 are different: meth, F, pro, and bute. And so we'll practice with those. And you'll find that this is not bad. Oh, you know what? Before we do that, I'm just going to give you a structure of, and just talk about chemical structures right now. This would be 5 carbons in a row. So that would be pentane, 5 carbons. The structure, the chemical formula would be C5H12, and the 12 H's come in, because remember, H's only have 1 electron. They can only make 1 bond. So the carbons can make, generally in organic, every carbon in every molecule is going to make 4 bonds. Sometimes there'll be double bonds to one thing or whatever, but they'll all make 4 bonds. Hydrogens will make 1. So the hydrogens go all the way around it. And hydrogen is always on the outside of the molecule because it can only make 1 bond. All right, so that would be the structure of the pentane molecule. That's tedious. To write all those H's individually, who wants to do that? We got other things we can do, like watch SpongeBob sometimes. So I can't be drawing H's constantly. So we can often condense it like this. Well, I'll even show you. Normally, I will draw organic structures with the carbons just with an H after it and however many H's it has. You'll have to choose what you like to do the best and what you're comfortable with. If you want to see all the H's and all the bonds, then draw it for yourself like this. But this is fine too. This and this are the same thing. Another thing you can do is leave the dashes out of it because we know that they're bonded to each other. Now, based on how many hydrogens there are, we can even tell that they're all single bonds, even though we don't see the lines. Because every carbon needs to make 4 bonds. So if this carbon has 2 hydrogens on it, 1 above and 1 below, it can only be making single bonds. Another way to even condense it more, we have 3 CH2 members of this chain. We could just do it like that with a CH3 at the end. So these are all the exact same molecule. They're just representations of it differently. This is considered to be a saturated compound. I'll have the term saturated on the next slide. But it's saturated because all the bonds are single bonds. That's all that it means to be saturated. So if that was intimidating you before, that's it. The simplest molecules are all straight chain hydrocarbons. Hydrocarbon just means there's hydrogen and carbon in the compound. All the alkanes will have this general formula. CN, N is however many carbons, and then based on however many carbons, there's 2N plus 2 hydrogens on it. some terms on this one. And again, tell me if you can't see that very well. Is it still okay to see? There'll be at least one double or triple bond somewhere in the molecule. So yeah, I'll talk later in the hour about unsaturated, but alkenes and alkynes are unsaturated. And I'll talk about why those are, but a saturated, the alkanes are straight chain carbons. They're really the most uninteresting because there's nothing to them. I guess uninteresting may be good because it's simple, and simple is okay, but you just count how many carbons are in the string of carbons, and you name it based on the slide that you had yesterday. If one of the hydrogens anywhere on the chain is taken out and something different other than hydrogen is put onto the carbon rather than the hydrogen, that would be considered a substituted hydrocarbon. And I gave you a couple examples. We're not going to name those right now. Later on in the hour, we'll name that. This is a couple days from now with something other than C and H. But that would be considered a substituted carbon. And I'll talk about what those substituted things are and how we name them in a moment. Those substituting things that come off as a branch from a carbon chain are called functional groups. And a functional group that's on a chain will alter the properties of the molecule. So, you know, if you have a hydrocarbon that's got a certain boiling point, you put a functional group on it, its boiling point's going to change. And maybe it's going to make it a polar molecule where before it was a nonpolar molecule. Yes? No, I think any functional group that you put onto a carbon chain is going to affect the properties. Yep. Maybe not much, maybe just a small amount, but it's going to make something different. So this horizontal chain of carbons, looks like there's 6 carbons in a row. So that was a hexane molecule, but now the hexane has been substituted. There's a methyl group, I keep moving that. A methyl group now that has attached itself. Notice the carbon there that it's attached to. It had 2 hydrogens before, but now it only has 1 because that CH3 has replaced one of the H's on that carbon. This just says that there's other functional groups other than hydrocarbons. You could have OH that's on there. That's called a hydroxyl group. It kind of looks like the hydroxide ion from what we learned last year, but this is not charged. It's just a neutral OH that goes on. We'll talk about that a lot later. Amine is an NH2 that is a functional group off of the chain. And there's other ones too. I've given you a couple just examples of them. One thing that I've always found strange is that we call any branch on a chain of carbons a functional group. The word group implies something plural, like there's more than one. I can see how a methyl group, you've got this cluster of atoms on there. But even the Cl, we call that a chloro group. Even though there's only one of them. I find that strange, but it's still considered a functional group. So a functional group is anything that's coming off of a carbon chain that's not hydrogen. Okay, now here's a word, nomenclature. The word nomenclature is from Latin. It means system for naming. And this is the way that we name organic compounds. So we learned some of the root names, methane, ethane, propane, butane, all that. We're going to be naming, even when there's functional groups on there now, we'll always identify what I call the parent first. The parent is the longest continuous chain of carbons. So identify that first, and then identify any functional groups that are on there. Okay. Now when we have this compound, this is a substituted hydrocarbon because you have this chain of carbons, but then there's a non-hydrogen thing coming off of one of the carbons. Oh my gosh, it's going to write. Okay, good. So we first identified the parent on this thing, and the parent will be the longest continuous chain of carbons. That's those. What is the name of the parent? Well, let's see, 1, 2, 3, 4, 5 carbons in that parent, so we would call it the parent pentane. The parent name always comes at the end of the compound's name. So if it's substituted, you're going to have the pentane there at the end. That's why I did that. And then identify all the functional groups that are coming off of it, but we wouldn't just say it's methylpentane. We have to say where on the parent the methyl group is. If the methyl group were on this carbon, it would be 2-methylpentane. It's on that one, so it's 3-methylpentane. What if it were on that one? Okay, this is where you want to be careful.